exactly. It's exactly the same thing. Okay, now if you write these equations in states, and the reason why I took this model is because it's naturally linear, and these are the state equations. What I did here, and I will drop it I think in the next slide, is I modeled the load as an additional input. So you see this is not a single input, single output. I have two inputs, the voltage and the load as an input. And the states are the angular position of the propeller, the angular velocity of the propeller, and the current absorbed by the motor. Okay? And what is the output? Yeah, that's a good question. It depends. I mean, I don't know what I'm measuring on this motor. In this case, I assume the output was the position of the propeller. That is kind of unlikely, but you might have an absolute encoder on the propeller, so you might assume that the position, that the measurement is the position of the propeller. Now, if you compute the, yeah, you have an absolute encoder. This is not happening. It happens in industrial manipulators. So if the same motor, you put it on, instead of on a propeller, on an industrial manipulator, you usually measure joints with absolute encoders. So you actually measure the angle of each joint, okay? In that case, if you compute the Kalman observability matrix, it turns out to be like this, and just by looking at it, this is absolutely invertible. It's full range. So the system is completely observable. What does this mean? It means that if you have a manipulator with an absolute encoder, from the measurement of that absolute encoder, I can estimate even the current that is being absorbed by my motor in each instant of time, which is not obvious maybe in the first place, right? But it's true. I mean, this is telling you that it's true. I can measure the full state. I can estimate the position. That's obvious because I'm measuring the position. I can estimate the velocity. That's also kind of obvious because if you measure the position, you can guess you can also estimate the velocity, right? It's just a different derivative. But it's also telling you that I can measure the current. I can, well, not measure, I can estimate the current absorbed by the motor if I know the voltage and if I know the parameters of the model.
And the load. The most critical
no, not really, because this, well, yes, this is an input. Yes, you should know the load, of course. You have to know the inputs. Another thing I didn't mention, because I don't want you to think this is magic, these estimates I'm talking about, they will, of course, depend on the model. So if your model is correct, you will have a correct estimate. But if your model is completely unreliable, your estimate will be affected, of course, by this, okay? Now, if you keep the same model, but you change input, so you see now, you change output. Now I am assuming I'm measuring the angular velocity, not the position any longer, okay? Now you can guess what happens. It's actually very easy to guess what happens. If you measure the velocity, but not the position, will you ever be able to estimate the absolute angular position of the propeller? Or the arm in the case of robots? Of course not. It's like if you drive your car and you measure the speed of the wheels, by that you cannot know where you are, right? I mean, there's no way, and no, unless you knew where you started from. That's the whole story. But if you don't know where you started from, you cannot recover that information. The initial state cannot be recovered. In fact, if you compute the Kalman observability matrix, you see you have a column of zeros. So this is not full range. And more, we can even say more. What is the unobservable state? The unobservable state is certainly one of the elements of the kernel of this matrix. Who is the kernel of this matrix? The vector 1, 0, 0. First component, whatever, and second components have to be 0 because here you have stuff that is different from 0, right? So if the question is what is the structure of a vector that multiplied by this matrix gives you 0? The structure is star, whatever, random, then 0, 0. So this vector, this is the direction in state space that is not observable. And so actually, that's what you get, that you cannot observe theta. Theta is the first component. So this matrix is telling you that the first component of the state is not observable, which is obvious, because you measure velocity and you cannot recover your initial position from measuring velocity only. But still, it's telling you that you can measure the current, because the other variables are not in the null space of the observer of the Kalman matrix. And of course, you can do the same with measuring the currents. If you measure the current, this is actually very useful in underwater robotics. If your motor controller board allows you to measure, the fanciest solution is where you measure actually both the angular velocity of the propeller and also the current absorbed by the motor. If you have those measurements, then you can do a lot in terms of low-level control. Because as Andreas was mentioning, if you measure the current absorbed by the motor, you have a direct measurement also of the load. So if you have trouble like get entangled in seaweeds or whatever, you will tell immediately. So it's also very easy to do fault detection. If something goes wrong, your current will go up and you can tell. And if you measure directly the angular velocity of the shaft, this is also very useful because although we didn't go into the details yesterday, but I'm telling you now, actually the hydrodynamics, this basic hydrodynamics is telling us that the torque, the thrust that you produce by a propeller is proportional to the square of the angular velocity. So if you have, if you can measure the angular velocity of the propeller, or even better, if you can control, actively control in feedback the angular velocity of the propeller, you have a good way of calibrating the thrust that you are producing. Okay? So the best in marine applications, although it's not very common because especially cheaper motors don't allow you to do that, but the best would be to measure both the angular velocity and the current. You really don't care about the position. You don't care if the propeller is turned 30 degrees or 50 degrees. You don't really care about that. But the other two variables are necessary, or are likely to be necessary. Okay. Other good news, if you have MATLAB, MATLAB does all this for you. So you can compute the Kalman observability matrix. You can compute. This is the function. And this is something I didn't mention, but I will in a second. Unless you want to have a break, I don't remember what was.
Now would be a pretty good slot.
It would be a good, okay, because I still have some things I wanted to show you if I have the time. But maybe we have a break and then we'll go ahead.
Let's say we break for 5-ish minutes, just getting a little bit fresh air, stretching, relax.